Meta-analysis. Maybe you've got the idea that we're very keen on meta-analysis. It plays such an important role in open science and in all of science, really. The basic ideas are pretty simple, and we hope you like Chapter 9, which has lots of stories, covers the basic ideas, and has no formulas. So we started off back in Chapter 1 with this simple forest plot, which summarises graphically an imaginary meta-analysis of the results of 3 polls, each represented by its point estimate and its 95% confidence interval, and then the result of the meta-analysis is another 95% confidence interval, but represented by this diamond. So the point estimate is right here in the middle, and that's the extent of the interval estimate resulting from combination of these 3 results. And as usually happens, as we are very happy to see, this result is a slightly more precise estimate than any of the estimates from the individual studies. I'm on the original 2 groups page of ESCI Intro Meta-Analysis, and these are the data from the brain pictures study in the chapter. So we have 2 studies by the McCabe group and then another 8 studies by the Robert Michael group that I was a part of towards the end. Each study is an independent groups study. So in the first one, for example, a group of 28 saw the passages with no brain picture and rated them, and an independent group of 26 saw the passages with the picture of the brain. So we enter for each study mean, standard deviation and n for each of the 2 groups. That's all we need to calculate the effect size, mean 2 minus mean 1 there, and to plot the point estimate and the 95% confidence interval. And so here we have the forest plot that summarises all the evidence we have from these 10 studies. We can apply meta-analysis to a small number of studies, 2 is the minimum, or to dozens or hundreds. And we need to make a judgment as to how reasonable it is to put into a single integration of evidence these studies. And if we judge them to be asking a reasonably comparable question, then we can make up a forest plot like this. Now, one of the slightly strange things is that a very long confidence interval attracts the eye, but is much less valuable to us than a short confidence interval. So often in forest plots, we display by weight. Studies that have very small n and a long confidence interval, they get little weight, so a small dot. Conversely, studies, here we are, 274 and 255, one of the Michael studies, the 2 groups in this Michael study number 5, get a big blob to attract the eye because this is very strong evidence coming from a short confidence interval. We apply a particular meta-analysis model, in this case the fixed effect model, which boils down to being just a weighted mean of all these means from the individual studies. And here are the study weights, these possibly slightly invisible red numbers here, ranging from 2% for this small study down to 35.7% for this very big study. It's perfectly reasonable, in fact it's essential, that studies that have very large n, that give us quite precise information, should be weighted more heavily in our meta-analysis. So meta-analysis applies the fixed effect model to these point and interval estimates and comes up with this result represented by a diamond. So the estimate of the overall effect is about 0.07, with a confidence interval running from 0.01 to 0.125, represented by this diamond. Now, the fixed effect model, which produces a weighted average of these means, assumes that each of these studies is estimating the same underlying population effect size. Is that reasonable? Well, in the real world, when every study has its idiosyncrasies, that's possibly not very realistic, but we can always calculate it anyway. That's the fixed effect model. We do have an alternative. It's the random effects model, and if I click down here, the radio button, instead of fixed effect, I click random effects. Note the difference, so fixed effect, random effects. Random effects, this result shifts a little bit and it's a bit longer. The random effects model allows for the possibility that these different studies might be estimating somewhat different population effect sizes. And if they are in fact estimating different population effect sizes, we say this set of studies is heterogeneous. And the more these point estimates bounce around, then the greater the heterogeneity. So fixed effect, we have a shorter diamond here. Random effects, a longer one. And also note that the weights change. And so these numbers here change and the sizes of the squares change as I switch between these two models. And that's because the models combine the studies slightly differently because they make different assumptions about the underlying population effect sizes being estimated. Let me say that again as simply as I can. For the fixed effect model, we're assuming that every study is estimating some particular underlying population effect size, and our best estimate of that is the centre of this diamond here, about 0.07. The random effects model acknowledges that there might be heterogeneity in these results, that these different studies might be estimating somewhat different population effect sizes, and under that model, we estimate a slightly larger population effect size of 0.09 with a slightly longer confidence interval here. Which model should we use? Well, virtually always the random effects model. But the point of mentioning fixed effect and random effect is that if we click between them and we find absolutely no change, then that indicates there's probably relatively little heterogeneity here. But if there's a very big change, if the random effect diamond is much longer than the fixed effect diamond, then that's evidence we have considerable heterogeneity. And in fact, the extent of change in this diamond is a very useful estimate of the amount of heterogeneity. And it's summarized by this figure here, the diamond ratio, which is simply the ratio of the length of the random effect diamond divided by the length of the fixed effect diamond. So if I switch between these, does this long one seem to you about 1.4 times the length of the short one? That's what the calculation is here. And that suggests that we do have some evidence of some heterogeneity in this set of studies. They're likely to be estimating somewhat different population effect sizes. And that's very valuable to know because we can use that information to try to tease out some further conclusions from our meta-analysis. The main conclusion is here is the overall estimate, more precise than any of these, and so this is our best estimate from this whole set of 10 studies of the population effect of a brain picture on the credibility of these different passages that we study in these experiments. But there will be more.